We have a review problem up here. You have the integral square root of t over 1 plus t cubed dt, and we're asked which substitution will result in an integral from our collection of basic integrals, because I said there's like 8 integrals that we know how to do. Our goal is move towards those 8 integrals. So is there a substitution we can make that gets us to one of our 8? There are some options here. T cubed, 1 plus t cubed, t to the 1/2, t to the 3/2. And then there's a 5th option, because we had to have 5 options. It says none of these really work. There's no such substitution available to us. What's the answer?
D.
The answer is D. T to the 3/2. Now, there's a comment in the corner. When you're looking for a substitution, look in one of 2 places. Either a function and a function. However, functions and functions can sometimes be obfuscated. So you have to be careful. The other part is to say, hey, is there something that I can integrate easily? So I marked this because we're in this second setting that it's a little bit easier to spot in this setting. So for reference, I marked down what would happen if you did each one of these substitutions and work them out. If you did the substitution A, you get 1 over square root of u times 1 plus u. That's not on our list. If you did B, you get 1 over square root of u minus 1 times u. That's not on our list. If you did C, you'd end up with u squared over 1 plus u to the 6th. Again, not on our list. But with D, you end up with 1 over 1 plus u squared, which is a happy integral. One of our favorites. That's an arctangent. That's on our list. And so for reference, this was what the integral turns out to be. All right. Good. Any questions? All right. This one would be hard if you actually went through and did all of the work to the end. Usually, you get the hang of saying, let me look for either a function and a function or a part with an easy antiderivative. And with practice, you can usually find that substitution fairly quickly. It's not going to be automatic. It takes practice. But the good news is you're just starting on your calculus journey. You've got the end of Calc 1. You've got Calc 2. You've got Calc 3. Maybe you're really lucky. You get to do differential equations. By the time you get to the end of your journey, you're going to be pros. You're going to be experts at it. All right. So today, our thought for the day, Wayne Gretzky, probably the greatest hockey player of all time. You miss 100% of the shots you don't take. And of course, someone might say, couldn't you also say you make 100% of the shots you don't take? Isn't that also true? All right, I'm not going to argue there. But what's the point? There's a tendency that we don't want to get out of our comfort zone. Because we don't want to be wrong. We don't want to make mistakes. So we tend not to take risk. We tend not to try weird things or try different things, new things. But if you stay inside your comfort zone, you're not going to grow. College is a time for you to grow. This is an ideal time for you to say, let me try new things. And this includes, how do you approach math problems? Try something. It may not work. That's okay. You probably have learned something, and then you can try something else. So take some risk in some sense. And on an exam, I shouldn't say this. This is, as a grader, I would discourage you from writing anything down because it's really easy to grade empty answers. But from your perspective, you should try something on all the problems. And I think there's some fairly reasonable problems. Even my problem is somewhat reasonable. We can talk about which one is mine after the test. I can give you a spoiler alert. Man, I wish. Arc sine. No. Never. Never. I'm sorry, but I have my standards. But mine is the one without parts A, B, ... That's mine. All the rest of them are like, I want to ask them like 2 questions or 3 questions or 4 questions. So, okay. Let's practice some more. Because there were some problems that we didn't get to, and I wanted to try some out. All right. The integral of 1 over t log t. What do we do? What do we do? So what? Okay, so we've had a suggestion, u equals log t. All right. That sounds like a great idea. Now, what makes u equal log t, what even suggests u equals log t is something to try? Because if you, think about what pieces you have. So you really have there's this multiplication I can think of it as like I have a 1 over t and a 1 over log t, and then like, oh, wait a second, 1 over t, that's ringing a bell. 1 over t is the derivative of log, and like, what? There's a log here. This is a match made in heaven. Okay, so let's see what this would become. If u equals log t, what is du? 1 over t dt. So this will become the integral of what? One over u, that's a 1 over u, and then this t becomes part joined with the dt of du. Do we know the integral of 1 over u? And by the way, let's just pause to celebrate that this is a good substitution. How do you know a good substitution? It's a simpler problem. The goal of substitution is to make things simpler. If you have a substitution and things get more complicated, 95% of the times, that's not a good substitution you just made. We're always thinking, how can I make it simpler? All right, integral of 1 over u. ln of u, natural log of u. Anything else? Plus c. Okay, are we done? What else do we need? We got the plus c. Yeah, we got to go back to where we started. We started with t's, we must end with t's. So, replace the u by what u is. So this is log of t. Log. Now are we done? Yeah, we did it. We took the antiderivative, we got back in terms of t. Life is good, life is wonderful. All right, let's try one more. I feel like there's a lot of space we could have used. Maybe we should have written things bigger. Log t plus c. There we go. It was a big problem. Now, it does say log of t. It's one of those things where if you hold it like at an angle, and then
it's like when you're driving.
And it looks more like log. Okay, all right. So let's try another problem. X plus 1 quantity squared over x squared plus 1. Now you might say, oh, x plus 1 quantity squared, isn't that just x squared plus 1, so we get 1?
Oh, that's right.
Or is there more to it, perhaps? All right, so what do we do? FOIL. Okay, so expansion. That sounds good. Do algebra. It's one of our favorite things. Now, there's not a clear substitution to make. X plus 1 doesn't look like it's going to really help us. X squared plus 1 doesn't look like it's going to help us. But algebra is always an option. So if you take x plus 1 quantity squared, what comes out? X squared plus 2x plus 1. All right. Cool. Now what can we do?
Separate x squared plus 1 and 2x.
All right. Someone has suggested there perhaps needs to be some separation going on here. Notice we have an x squared plus 1. So we could rearrange this and say, this looks a lot like x squared plus 1 plus 2x over x squared plus 1. Or just thinking about these as breaking up using our nice plus sign upstairs, the good kind of plus sign, we can split this into two pieces. X squared plus 1 over x squared plus 1, also known as 1. Plus 2x over x squared plus 1. Okay, so what can we do now? And again, we haven't done any integration. All of this is rewriting. We're moving towards getting to places where we are like, we have things we can integrate. Okay, we have, good. I was hoping someone would fall into the trap, but no, someone said, we're not falling into that trap, Steve. We can split this into two integrals. There's a subtlety here, and but you are correct. We do want to split this into two integrals. The integral of 1 dx plus the integral of 2x over x squared plus 1. Now, let's go a little bit farther, and then we'll talk about why we wanted to do that and why we had to do that. Are we able to do either of these integrals right now? We can do the integral of 1. What's the integral of 1? X! Yes! It marks the spot! Nice! Okay. Now, what about the second integral? What can we do there?
Pull 2 out of it.
We can pull 2 out of it, but what else can we do? What substitution should we make? If you said u down here, and I know you're like, but Steve loves arctangent. Is he depriving himself of an arctangent? Yes, sometimes for the greater good. Root of x squared plus 1, 2x dx. So, I'll write this as du over u. What's the integral of du over u? ln. Good. X plus log of u plus c. Is that our answer? No. How do we get to our answer then? Plug u back in, which becomes x ln of x squared plus 1 plus c. And there we go. Now, a couple things happen here. We did algebra to work on rewriting, and we split it up. So I want to talk a little bit why this was important. And I'm going to put the word important here next to it to emphasize that this was an important step. So why did we have to split up? Couldn't we have just made a substitution at this stage? The answer is no. Because we could have said u equals x squared plus 1. The problem is this did not have a 2x available to it. So we couldn't finish the substitution with this piece in it. But by separating it, we can say, look, I can now think of it as two separate sandboxes. I guess there's a term, computer programming, where you're just saying, look, I'll think about these as completely different integrals that are no longer connected together, so I don't have to do the same thing. So I can make one set of choices for the first one. In this case, it's like, my set of choices is just I know the answer. And a different set of choices for the second one by making a u substitution. You can even have cases where you might make different choices, like different substitutions depending upon which part you're in. But all right, so there we go. Fun problem. I guess one other thing to note is you start to recognize certain things. So one of the things you start to recognize is when you see 2x over x squared plus 1, it probably suggests a log, because if you think about the derivative of the log of a function, do you remember what that turns out to be? It's function downstairs, derivative upstairs. So if you ever see a ratio and like, oh, if I take the derivative of the bottom, I get the top, you're like, that's a log, and you're a quick substitution away. So log turns out to be very useful. It shows up very frequently. So it's one of those ones it's good to have in your pocket for when we're ready to use it. All right, so that was our practice with what we did last time. But we want to talk about not just substitution for indefinite integrals, or if you like, substitutions for antiderivatives. We have a whole other category, which is substitution for definite integrals. Now, I know there's a lot of text here, but it actually says a lot less than you think. Let's just make some recalls. When we have definite integrals, that includes bounds. It says you're going in between two things. But oftentimes what we suppress is our notation. So when we write integral a to b of f of x dx, what we're not writing is that this a actually means an x value. X equals a. This b, again, is an x value. X equals b. So we're going from x equals a to x equals b of f of x dx. Now, when we talked about substitution, the name of the game is update all the places where the old variable occurred in terms of your new variable. So when we were doing our substitution before without the bounds, we said, well, you have the g of x becomes your u, the g prime of x dx becomes your du, but the only new change is update the bounds. So you start with x bounds. You cannot stay in x bounds. You've got to move to u bounds. So you say, well, what is it in terms of u? And here's the great aha. You say, well, look, I know what x is. I can plug it in, and then I have u, and then I put it as my new bound. So if I start at x equals a, I say, well, what's that correspond to in terms of u? And the answer is it's g of a. Same thing. If x equals b, plug it in. What does it correspond to? G of b. So you update your bounds. Now, this is a very long way of saying you have two options. One option, which is this is preferred. You should go with this. It's the one I strongly encourage you to adopt, which is always update your bounds. Now here's the cool thing. If you update your bounds, you don't have to go back. So if you start with x, rewrite your integral in terms of u, and you have your new bounds in terms of u, then when you evaluate, you just use your new u bounds. So there's no going back. Why does this work? Well, because it saves you time. We like doing the least amount of work possible, because the less work we do, the less likely we make mistakes. Now, that's one option. The second option, well, it's like, I don't like bounds. I don't want to update them. I'm just going to drop them, and then I'm going to find my antiderivative, put everything back in terms of my original variable, and evaluate. You'll get the same answer if you can do it. There are some cases where you won't succeed. And we'll see one very soon. So I would say always update your bounds. On a side note, if you do not update your bounds, that is an easy place where people take points off. And I know I talk about, we don't want you to lose a point. I'm not obsessed with wanting you to get great scores on your exams. I just know I don't want you to lose silly points. If you're going to lose points, lose non-silly points. So make sure you do update your bounds. All right, so moral of the story, we could summarize all of this in just saying, if you have a definite integral, update your bounds. That's today. That's the lecture of today, that one sentence. Any questions? Then the rest of today is just practice with that. All right. So, here we go. Find the integral from -2 to 9 of 2x minus 7 e to the x squared minus 7x cubed dx. Okay, so first off, we're going to do this in two ways. So I want to start with method 2, which is drop the bounds, and then see how far we get. So if we do that, then our real goal is to say, let's find the antiderivative of 2x minus 7 e to the x squared minus 7x cubed. What can we do? There's a suggestion for you. What was it?
U is x squared minus 7.
U is x squared minus 7x. That's definitely an inside part. And what else do you notice about x squared minus 7x? Yeah, you see the derivative of x squared minus 7x just sitting there, right for the taking. It's like it's trying to wave at you. It's like, make this substitution. This is the way. All right, so u equals x squared minus 7x. du is 2x minus 7 dx. So then this integral becomes what? E to the u cubed, because there's a cubed here, du. All right. Now, at this point, what should we do? Bum, 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 bum. We're toast. Not going to work. Can't integrate this. Not because you're not cool people. You are cool people. No one can integrate that. Well, that's method 2. What haven't we done yet? Method 1, which says, hey, use the bounds. So we're not going to change the substitution. And at this point, you're like, if you're not changing the substitution, you're still going to run into the same problem, Steve. Have faith. Let's just try it. Okay, so these are x bounds. X equals 2 to x equals 9. The inside part, nothing differs. So it's still e to the u cubed du. The difference is we need to update the bounds. So if we plug in -2, what comes out? So negative 2 goes into which one of the formulas? X squared minus 7x or 2x minus 7?
X squared minus 7.
Goes into the x squared minus 7x. So we can do some little computations down here. Negative 2 squared minus 7 times negative 2. Negative 2 squared is also known as 4.
So 18.
And negative 4 times negative 2 is 14. So that also looks a lot like 18. Okay. Now, plug in 9. We plug 9 into the same formula because we're updating the bounds. What do we get for our upper bound? 9 squared minus 7 times 9. 81 minus 63, which is 18. Okay, so question. Do we know what the integral of e to the u cubed du is from 18 up to 18? 0. Yes. And we're done. So there are certain things that we can't find the antiderivative, but we can still find the value for. One of them is if our bounds match. So secretly there was symmetry going on, and there was cancellation. It just was hard to see there, but super easy to see here. So essentially there's hidden symmetry. So that's why be careful. Dropping bounds might get you stuck, whereas if you just kept your bounds, things might be easier. Okay, let's try some more problems. Okay. Find the integral from 0 to pi fourths of secant squared theta, tangent theta, d theta. And here, it's going to tell us our substitution, so we don't have to guess. But it's going to say, do it twice. So this is a problem so nice, we're going to do it twice. All right. So it seems reasonable we should start with part A. U equals tangent theta. Well, if U equals tangent theta, what would du be? Secant squared. So our integral is 0 to pi fourths of secant squared theta, tangent theta. We can just rewrite it a little bit. Tangent theta, secant squared theta, d theta, just to emphasize what's going to happen. The secant squared theta d theta becomes our du. The tangent theta becomes our u. So this becomes integral u du. But what are the bounds? So it used to be 0. Now that's a theta bound, not a u bound. So the theta bound was 0. So what is our new u bound? Which is also known as 0. Yes. You might say, Steve, that's the same thing. No. This is theta equals 0. This is u equals 0. It looks similar, but there's a difference. Okay, what about our top bounds? 1. Tangent of pi fourths equals 1. What's the integral of u du? 1/2 u squared. Evaluate from 0 to 1. So we're using our fundamental theorem of calculus. We took an antiderivative, now we do an evaluation. See, we're not going back to theta. We use our new bounds. When you plug in u equals 1, what do you get? 1/2. When you plug in 0, what do you get? 0. So the answer is 1/2. All right. So when we substituted tangent, we got 1/2. Oh, but what's going to happen when we substitute secant? Any predictions? Yes. We know it's going to be 1/2. If we got different answers, it doesn't mean we broke math. It means we made a mistake. However, the moral here is the journey may be different. So let's enjoy the journey. So, part B. If u equals secant theta, what would du look like? Secant tangent. Derivative of secant is secant tangent. So secant theta, tangent theta, d theta. All right, so this would become integral of, so let's first off rewrite it to be set up. So I'm going to think of the secant squared as really a secant times a secant. So I have secant theta times secant theta, tangent theta, d theta. So the last part, that's our du, and the first part is our u. And you're like, what? It's the same integral. Or is it? We do get u du, but what will our bounds be? Plug in 0. Does anybody know secant of 0? 1. Okay, now the real challenge. Secant of pi over 4. Square root of 2. Oh, you guys, that's awesome. I was prepared to hum and haw for a minute. But no humming and hawing needed here. Okay. Do we know the integral of u du? Yeah, it hasn't changed in the last minute. Evaluate 1 to root 2. When you plug in square root of 2 squared, also known as 2. Minus 1/2, 1 squared, 1. So you have different bounds. So again, you might have different substitutions available. It might lead to different intermediate steps, but at the end, what does this become? It becomes 1 minus 1/2, which is 1/2. All right. Now, I feel like I haven't given you enough problems. So maybe this one, next one is yours. Find the integral 0 to pi fourths of 2 minus secant squared theta to the 1/2 times secant squared theta d theta. And I'll give you a hint, if that's okay. If you don't want to hear the hint, close your eyes and cover your ears. Hint. Tangent squared theta plus 1 equals secant squared theta. There's another hint. You don't actually have to integrate to find this integral.
Oh my God.
Pi fourths. Okay, so there's clues. Learn to read the clues. When you look at this, you say, there's a secant squared theta on the end, and you might say to yourself, this is the derivative of tangent. So that's suggesting we have to do a tangent substitution. But if we're going to do a tangent substitution, we need to have this look like tangent. But here's the cool thing. A secant squared is basically a tangent squared. Why? Because of this identity. So if you have a secant squared, it's just as good as a tangent squared, and vice versa. So we're going to replace this secant squared in terms of tangent squared. So 1 minus tangent squared theta to the 1/2. We do the u substitution. We get 1 minus u squared to the 1/2, which is the square root of 1 minus u squared. When we see those kinds of expressions, square root of 1 minus something squared, circle. And we don't do them by finding the antiderivative. We say, there's geometry. This is an area. So the area is 1/4 of a circle radius 1. So the answer is pi over 4. Now, this is a challenging one. So if you got it, great. If you didn't get it, that's okay. You're learning. You're learning to spot things. And with practice, things will get better. All right, one last problem for the day. Any questions on this one? We're good? Good times. Fun was had by all. All right. Find the average value of the function x squared over 1 plus x cubed in the interval between 1 and 3. So this is requiring us to know stuff. So for example, we have to remember things like average value. So, do you remember how to find average value? There is an integral involved. So average value will be mysteriously big gap here, integral a to b of the function.
1 over b minus a.
1 over b minus a, yeah. So usually when you do an average, it's like a fraction, something over something. Okay, so in our case, what are a and b? 1 and 3. They're the bounds. So we get 1 over 3 minus 1 integral 1 to 3 of the function x squared over 1 plus x cubed dx. What can we do here? Someone says, hey, look at this 1 plus x cubed. What's the derivative of 1 plus x cubed? A lot like x squared. And you're like, whoa, it's like there's a 1 plus x squared, there's an x squared up there, almost like they wanted us to succeed. Because we do. So du is 3x squared dx. Now, what do we do with this 3? There's a couple of options, but I find the easiest thing, move it across. So 1/3 du is x squared dx. Don't forget the half. So 1/2 integral, the x squared dx will have a du, and then there'll be a 1/3, I'll pull the 1/3 out. And then we have 1 over u. Is there anything else we need to do? Just our bounds. We're always updating our bounds when we do definite integrals. Our current bounds are 1 to 3. These are x bounds. We need to go to u bounds. So when x equals 1, what will u equal? 2. 1 plus 1 cubed. When x equals 3, what will u equal?
28.
28. Just rolls off the tongue. Right? 3 cubed is 27, plus 1 is 28. So this is equal to 1/6. The integral of 1 over u? Natural log u. Good. Evaluate from 2 to 28. So this is 1/6 of natural log of 28 minus natural log of 2. Can we do anything else here? It's good to practice our natural logs. We have a subtraction.
20 divided by, so I'll let it 40? Or 14, there you go.
Subtraction becomes division. So this is 1/6 log 14. So remember, we have our nice properties of logs. Log of a minus log of b. Log of a over b. Let's write a few others. Log a plus log b. Do you remember that? Log of a times b. Log of a to the power b. B log a. So know your properties of logs. You never know when they might be handy. All right, so 1/6 log 14. I think that's a pretty good answer and a great place for us to stop.